Okay, sorry. So I encountered a minor difficulty and I decided it was best to just split this into 2 lectures and start over with what I wanted to explain here. So this next sort of application of work that I want to explain is, let's suppose that we have like some object and we want to pump some liquid out of that container. And the container can be any shape that we want to. And let's suppose that we want to pump all of that liquid up to some total height of capital H. Well, how much work is required in order to pump this thing out? The answer is going to be, excuse me about that, the answer is going to be, I can't answer the question directly, but I can start approximating it because I can say, well, what if I split this thing up into a bunch of little layers? And we'll call the height here H. How much work does it take to lift just one layer of liquid up to the top? Well, the answer is that we move the layer a total distance of capital H minus little h. And then there's the question of, what is the actual force that we need to move this thing? Well, that is going to be the area of H times delta H times the density, which we write with this Greek letter rho. Rho is, it sort of looks like a P, times the force of gravity. And we move it this distance. So the work per layer is going to be the area times rho times g times capital H minus h times delta H. The total work is then going to come from summing these together. Now, here's where we're doing the approximation. So let me explain where the approximation is coming in this formula. See, really, I'm having to think of these as H stars, where H star is picked to be some height within this layer. And this is only approximated because technically the layer isn't at a fixed height. The top of a layer doesn't move quite as far as the bottom of a layer. Also, technically, the top of the layer may have a slightly different area than the bottom of the layer. But provided that we make the layer fairly thin, this gives me a good approximation. The total of these approximations will be the sum from I equals 1 up to n of the area times h minus h, rho g, delta h. In the limit, this is going to approach the integral from 0 up to the total height here, or however I choose to make my bounds. A of h times capital H minus little h, rho g, dh, sorry, not delta h. We're doing the integral now, so it is the differential. Okay, I then wrote dg. dh is what we're looking for. Okay, so this is how we go about doing this. And you'll notice that this is kind of a standard operation for us at this point, right? Standard operating procedure is we have something that we want to calculate, but the problem is we can't calculate it because everything is varying like mad. However, if we could approximate it as being constant over some small intervals, then we can approximate those using some formula and add up the results. That sum of the results, the sum of the approximation, is an approximation to the total, and it's also a Riemann sum. So as our approximations approach being completely accurate, the Riemann sum approaches being a Riemann integral. At this point, we've seen this happen many times. This is just the latest iteration of this. So I'm going to do a problem for you here that is kind of similar to problem 23 in your textbook. and show you how you can use this kind of thing. But I warn you, you do have to reason through the problems yourself a little bit, and you'll see why in this particular example. So let's suppose that our scenario is a triangular trough. And so it looks sort of like this. And let's say that it is 3 feet in height, 8 feet long, and it's 3 feet wide. Now, let's suppose that this thing is full of water and we want to pump it out. Now, water is 62.5 pounds per cubic foot. That is the weight of water, or the density of water. So when you're working with pounds and feet, you don't actually have to do density times gravity, because pounds is already measured in that way. And so when you're working, depending upon what kind of units you're working with, it just depends upon whether you have to do density as mass times gravity. When you're working with these kinds of units, pounds is already mass times gravity. In fact, this is something that's a little confusing. When you measure pounds, you are not directly measuring mass. Pounds is a measure of force. The conversion into mass, like the fact that somebody would say, oh, I weigh 200 pounds. Well, what that really means is at the surface of the Earth, my mass exerts a downward pressure on the floor of 200 pounds. It's not my mass. That is my mass times the force of gravity. So this is already the density of water times gravity. This is why units can be very confusing. And if we were in a physics course, we would be spending a lot more time on exactly making sure the units come out. But suffice it to say, pounds is a measure of force. Kilograms is a measure of mass, and you do need to do kilograms times the force of gravity. But when you're working with pounds, no problems. Okay, to make things a bit more complicated, let's suppose that instead of just pumping it to the top, we've actually got a little spout here, and the spout is an additional 2 feet above the level of the trough. So in other words, we're not just pumping a layer up to the top, we're actually pumping it 2 feet above the top. Now, here's what we're going to need to figure out. Let's take some little slice here and figure out what do we need to do to get that slice up to the top. So the slice moves 5 feet minus h, where, actually, let me put h over here. H is the distance away from the bottom of this thing that we move it. What is the area of a slice? Well, the area as a function of h is going to be 8 feet times the width of the slice. And what is the width of one of these slices? Well, we need to use a little bit of geometry in order to figure this out, because we have to figure out what are the portions here that we are talking about. Now, the thing is that the area is going to be, or the width here is going to be little h divided by this height of 3 feet times the width of this base, right? Because this little triangle down here with a height of h, this is similar to this triangle here with a height of 3 feet. And therefore, this width, w, excuse my terrible crowded drawing here, but the width, w, as a function of h, is going to equal 3 feet times h over 3 feet. The 3 feet cancel, and the width is actually equal to the height. Okay, now, that's actually a pretty nice result, but I wanted to show you how you think through this because that wouldn't necessarily always be the case. Depending upon the dimensions of this cross-sectional shape of the trough, we might get something totally different. So now what do? Well, we have the width of the slice and we have the length of the slice, so the area is going to then be equal to 8 times h in square feet. Those will be our units. The volume is then going to be the area times delta h. And the distance that we're going to be moving this thing is going to be 5 minus h. So we can now set this up. Now, I hope that you have this written down because I'm going to be erasing it here. So we're going to be integrating from 0 up to 3. The area, which is 8h, and then I need to multiply that by the height it moves, which is 5 minus h. Then I need to multiply it by this force density, 62.5. And finally, I need to multiply it by dh. Now, do the units work here? They do, because this picks up feet. These are both in feet. And dh is also in feet. So we've actually got feet cubed, which cancels with the feet cubed here. And so we're really just integrating pounds, which is what we want to do in order to make things work out for the work here. So again, the units can be a bit weird, but we do have to remember that dh is actually measured in feet because h is in feet. So there's actually feet cubed going on here getting canceled by the feet cubed. And now this is actually a fairly straightforward integral to do. So we've got the setup here, and that's all that we really need to do. I will leave it, well, we need to actually answer the question, but I will leave it for you guys to figure out how you can continue this sort of thing and set up the rest of the actual integral here. Actually solve the integral. Because at this point, you're just integrating a polynomial, right? So let's take a look at one other example of doing this kind of thing to sort of see how we can reason through it. What if this time, instead of having a trough shape like this, what if I have an inverted cone? And let's say that this cone is 6 feet high, and this is 4 feet wide, and I want to, once again, pump out water. And let's say this time I just want to pump it up to the top. No more spouts or anything like that. We're just going to pump this thing empty of water. Well, the distance that a given slice is going to move, sorry, that doesn't look much like a slice. That looks a bit more like a slice, is 6 minus h in feet. That's how far I have to move a given slice. Now, what is the area or the volume of a slice? Well, I need to figure out what is the area of this thing, and to do that, I need to ask myself, what is R of h? Well, R of h is going to be equal to, see, these have got equal ratios. So what we know is that R divided by h should be equal to 4 divided by 6. And that means that the radius is going to equal 2/3 of the height. Once again, I am using similar triangles here to do this. Now, for some of your problems, you won't be able to necessarily just solve it with similar triangles. These two examples, I've happened to use similar triangles, but that's not something that you can just say is going to happen every single time, okay? You're going to have to, think about the particular problem. Like, there's another problem in your book, problem 24, that involves a sphere. So there we have to do some other kinds of work in order to make things work out for us. But, it's all just use the geometry to figure out how do you find the area of one of these cross sections. And so the volume that we get, or well, the area is going to be what's important here. So the area is going to be pi r squared, which is going to be pi times 2/3 h squared, which is going to be, if I can figure this out, 4 pi over 9 h squared. Okay, that's good. We have that so far. And now we just need to integrate from 0 up to 6 of the area, 4 pi over 9 h squared, times the height that we lifted, 6 minus h, times the density, which is still just 62.5, times dh. And there's our integral all set up for us. So there we go. You can now complete this integral. You have to do a little bit of calculation in terms of what do all these numbers simplify to, and then you just have to integrate basically a polynomial. Once again, to check that everything makes sense, we can double check here that our units are working out. So in the previous one, I think I said that we had feet times feet times feet, and I think we actually had an additional feet thrown in there. We actually had feet to the 4th, which is what we wanted. This one also, we have feet to the 4th here, and all the units end up working out for us. So, this is a volume, and then we have the density, which is weight per volume, and that's really what we want. We need volume times the force per volume so that it cancels. So once again, the units work, and that's just a good way to double check. Okay. So next what we're going to do, I just want to kind of think for a moment about different ways that you can come up with areas of cross sections and things like that. Because other than finding the area of the cross section, most of these are just about reasoning how far do you have to lift that cross section in order to get this done. So to give another example, what if I were trying to find the area of, let's suppose that I had a sphere. Suppose I had a working pen. And let's suppose that the total height of this sphere was, let's say, 10 feet. And I wanted to know the area of a cross-section of height h. Well, there's different ways of trying to figure this out. But what I would do is I would actually say, the first thing is to say, I'm not going to treat h as the distance from the bottom. I'm going to actually set h equals 0 to be along the center of the sphere. So h is going to be my height from the center of the sphere to my slice. And that means the bottom is going to be at h equals -5, and the top will be at h equals +5. We're allowed to do this. We can make these variables be whatever we want to make it the most convenient for us. Now, why is this convenient for me? Well, the reason is because I can now think of the radius here and the height as being the base and the side of a right triangle, and that right triangle is going to have the same radius as the sphere. But the radius of the sphere is 5 feet. So what this is going to give me is it's going to give me that the radius here is equal to the square root of 5 squared minus h squared. And that means that the area as a function of h is going to be equal to pi times 25 minus h squared. Because remember, the area is pi times r squared. So this gives me the area of one of these slices. Now, what I encourage you to do is go ahead and take a look in your book at problem 24. It's not exactly this problem. The dimensions are very slightly different, but it does involve pumping out a sphere just like this. And this is sort of the key step. Everything else in the problem is going to go the same way as the examples we've done so far. But this one key step is where you need to think about things a little bit differently. So the area of a cross section at height h is going to be given by a formula very similar to this. See if you can work that out. If you can work that out, then you should be able to hopefully finish the rest of the problem. If you have any questions about that problem, feel free to let me know. All right, so that covers a lot of the stuff we want to say about work and integration. And as you can see, integration doesn't just come in when we have to integrate a changing force. That was kind of our first example. But it also comes in when we're moving different parts of the object different amounts. So this is another kind of thing that we can ask, like, how much work is it going to take to pump this out? That's important because the work is related to energy. So if we want to know, like, how much energy is it going to take us to pump this thing out? Well, yeah, that's important. That's really what we're looking at here. So again, this is not necessarily something that's maybe a thing that you're going to study a lot. Not all of you are going to be doing physics. But we're showing you these things because it's more about learning how you think about these problems than it is about learning how to do these specific problems. It's about learning how to take a thing, how to take some situation and think about, okay, we can't calculate the result exactly, but we can do an approximation using a Riemann sum, and then in the limit, that becomes a Riemann integral, and we can calculate the Riemann integral exactly, at least if the function is a nice integrable function, if we know how to find the antiderivative in particular. So it's about learning that process of thinking through the problem and using that process to take a problem, turn it into a Riemann integral approximation, and turn that into a definite integral. All right, so we'll continue looking at some applications of integration in our next lecture, which will hopefully occur in one part because hopefully I won't have to stop in the middle. See you in a couple of days.